So I'm going to talk about the Arrow project. Set myself a little timer here. And I'm gonna, as I mentioned, I guess I just gave an overview of what I'm going to talk about, but I'm going to kind of go through some of the use cases of Arrow, how it's grown since its creation. We had a milestone of reaching a 1.0 release this past summer. So I want to talk about that kind of growth trajectory and then where we go from here. About me, I lead the engineering team at Ursa Labs, and we are Ursa Labs is a consortium that's funded by multiple companies. Our studio is one of our leading funders, to basically to grow and contribute to the maintenance of the Apache Arrow ecosystem. And I'm really excited. This is actually the first time I can say this. We've also just announced this morning, that we've raised a seed round of funding to expand what we've been doing with Ursa Labs to Ursa Computing, to be able to offer more services and products on top of Arrow, while also pulling forward and continuing with our labs mission to sustain the open source project. So Arrow was created in 2016. A group of database developers and data frame library creators decided, they got together and realized they were all trying to solve similar problems. And so rather than duplicating their efforts, that if we work together and create a kind of a shared foundation, that we would all benefit. They would decide that this was not fine and we can do better. So Arrow is three things fundamentally. First is there's a language agnostic specification of how bits are arranged in memory. It's columnar, and it's designed to take advantage of modern CPUs and GPUs and things like that. There are also 12 libraries within the Apache Arrow project that include either an implementation of the Arrow format or are a wrapper around another implementation. So Python, R, Ruby, all are wrappers around the C++ implementation of Arrow. But Java and Rust and JavaScript, they're their own independent implementations. And we have integration tests that ensure that they are faithfully implementing the same standards so that we can communicate evenly and fairly. And we recently, a couple months ago, added our 12th library, which is the Julia Arrow library. And then around all this is the ecosystem of projects that use Arrow in some form, whether it's as a means of exchanging data or as their internal data structure. And I'll show how this comes into play in a minute. The Arrow project has grown and continues to grow in adoption. We crossed 10 million downloads a month just with the Arrow the PyArrow Python package off of PyPy, which is, we have many languages, and obviously there's other ways that you can download even the Python library, but this is, I think, an indication of the gradual uptake of Arrow and how it's being increasingly adopted by projects in the Python ecosystem in particular. I want to walk through a few things that you can do with Arrow now, and if you, I should have said this at the beginning, but I have posted these slides online so that you can follow along if you want, and also I've got a lot of links to other things that we've done. And so I'm not going to go through them all in detail, but they're there for reference on your own time. So one thing that's big in the C++ section of projects, I maintain the R package, so I'm going to show some R specific things, but they are all features that are in the C++ and thus Python and R libraries. One big feature that we've been developing this past year is the ability to work with multi-file data sets. If you're, I know someone's going to talk about Dask in a minute, and so Dask also lets you do this kind of thing. And this is a different version of that, but with some different performance and other objectives. So from R, I did a demo of this about a year ago of scanning 2 billion rows of data split across 125 files using what is basic dplyr syntax for R. If you're familiar with that from R, and getting a result really fast. Now, when I did this demo initially back in January, it took 4 seconds to do this query. And just doing it again last week, it was 3 times faster than it was just at the beginning of the year. And this speaks to the volume of activity in the Arrow project that leads to kind of a sense of continual improvement. Like I said, I maintained the R package, but I didn't really do anything that contributed to this speed up. This is coming from lots of other parts of the Arrow project. In general, our readers and writers for various file formats are also very fast. Parquet is a popular columnar file format, as well as Feather, which is actually the Arrow memory format persisted to disk. So naturally, we read those. But doing some research earlier this year, I found that actually our CSV reader is incredibly fast. Literally incredibly fast. I presented it to some people and they did not believe that it was possible to do this fast and be this fast in R. I did some benchmarking here, and in which you can see more there. Just a glance at the results. I added some variations that used Arrow to the suite of benchmarks that the Vroom package for R provides, which benchmarks a bunch of CSV readers. And just focusing on the Arrow ones, you can see that they took, in general, much less time to complete than the other R packages. And interestingly, this part here just zooms in on reading a CSV into an R data frame. So, the bottom bar there is where I did work using the Arrow computational libraries, which are, as you can see, very fast. But even if you just use Arrow as a CSV reader and then can do whatever other R packages to analyze the data frame afterwards, it was still, 2 to 3 times faster than the fastest CSV reader otherwise in R. So just as a drop in there, you can save seconds from each read there, which is pretty great. I pay attention most to the R stuff because that's what I work on, but there's a lot of other activity in the Arrow project. There's been a lot of activity in the last several months, particularly in Rust. We have a query engine with some SQL support in Rust that's got some pretty impressive benchmarks as well. So if you do this type of data analysis and like to use Rust, we've got tools for that. Another really exciting framework is Flight, which uses gRPC to move data across the network. So it's a client server framework that lets you send data. We've clocked it at over 3 gigabits a second within the local network, pushing data. So this lets us get closer to local reading speed, but it's data over the network, which has a lot of great potential. There are a number of projects that are based on Arrow that have Arrow at their core, and I want to talk about a few of those. So first, I think it's come up a few times at this workshop here, is the Rapids project from NVIDIA. They have a series of CUDA-enabled libraries to do, whether it's machine learning, and it's cuML, and then there's cuDF, which is a data frame library that's built on top of their GPU libraries. And those all use Arrow internally as their data format because, as I mentioned, Arrow is designed to be efficient for modern hardware. And I actually, for those who are curious, the benchmarking that I just showed about the CSV reading, I did a version calling the cuDF library from R, which was a fun experience to do that. Recently, InfluxDB announced that they are rewriting the core of their database in Rust using Data Fusion. And so this has been a great source of energy in the Apache Arrow project of late with their contributions and really pushing what is the performance boundaries in Rust, which is very cool. And this is a JavaScript based, it's a browser based use of the JavaScript implementation of Arrow called Falcon. You can go to that URL there and play with this. And it, because the Arrow format is very efficient, it allows you to actually hold a lot of this data and work with it quickly in the browser. There's some really impressive numbers on their website there of what the largest data sets they've worked with in the browser, which is quite cool. But Arrow is largely designed. One of the design goals of the Arrow libraries is that they're developer tools that you, as a developer, can use Arrow to as a way of speeding up your workflows in your libraries, with data access to other services in a way that maybe your library users don't know that they're using Arrow. And it reminds me of this. This is probably showing my age, but the chemical company BASF had this ad campaign in the early 90s where they said, we don't make a lot of the products you buy, we make the products you buy better. And that's a common, it is true of many applications of Arrow that are out there. So for one, if you use pandas or use Dask to read Parquet files, you've probably used Arrow, and you may have been aware of that, but you may not have realized that's what you were doing, because the Parquet reading functionality that's in the C++ and Python and R ecosystem is part of the Arrow project. Another place this comes in is with accessing different data sources. So towards the beginning of the Arrow project, one of the first goals was to make efficient data exchange and user-defined function evaluation in Python using Spark. Now, this takes advantage of the fact that Arrow involves this format that is language agnostic. So Spark is in Java, and they use the Arrow Java library, and PySpark, obviously it's Python, and uses the Python Arrow library, and they're able to communicate really efficiently. And so again, 10x, 30x, 100x speed up in pulling data from Spark or pushing data to Spark just by using Arrow. Again, because it's a standard like that. Once you've got it in one, it's easier to add it to others. So we did the same thing in R a couple of years ago. And again, you just load the Arrow package when you're using the Sparkly R package, and you just get these speed ups, and that's all you have to do. BigQuery also lets you has a way for shipping results using Apache Arrow, and they've also found some big performance wins from that. And as I mentioned, the key to this is that the format is language agnostic. So if you think about what you otherwise might do, so you want to connect Python and R to Spark, you could write something that is not language agnostic, that is specialized, so that Spark can write to R's internal memory format, and it can write into the Pandas internal memory format. That's a level of complexity that I personally wouldn't want to do, but you could do that. And the number of connections here is not that great. But when you start adding more projects and more languages, it gets crazy pretty quickly, the number of connections you have to make. And so you're not actually going to do this. What you're really going to do is you're going to have a standard format that is your means of exchange. Unfortunately, what this prior to Arrow leads to is using an inefficient format like CSV, which is slow to read, slow to write, involves translating your columnar binary format to a row-based text format that has all the parsing that comes with that, to say nothing of the lack of rich types and stuff that comes with CSV. So Arrow facilitates this because, for me as the R package maintainer for Arrow, once we've implemented the, being able to efficiently get data to and from, between Arrow memory and R memory, now I can connect to Spark. Now I can connect to BigQuery. Now I can connect to Python super efficiently. I don't have to adapt a special connector for each one. So the Arrow project, as I mentioned, it started in 2016, and I realize I'm running out of time, but I'll blow through here quickly. Earlier this year, we hit the 1.0 release, which I think marks a new level of maturity of the project. It's, we're going beyond kind of the early adopters, and now we're at a point where I think a broader swath of the developer community is perhaps ready for Arrow. And as you can see, the number of contributors to the project has really grown over the years and continues to climb. And so, Ursa Labs has really played this role of being a maintainer, but that is something bigger than just one person, that we collectively can play this role. But we wanted to see what we could do to support and sustain the community going forward. And what are the needs of this community growth now that we've reached this milestone? And so one of the things we want to do is find a way to grow the maintainer base, not just the contributors, but the people that are going to be around to make sure the packages compile on the different platforms and that we do a release successfully and all of that. And what we found is that, or what my analysis, what I found is that and I don't think this is unique to Arrow, but it's perhaps, I feel like we experience it in an extreme way. You have a lot of people, we're very welcoming of new contributors. So you get a lot of one-time bug fix contributors or documentation contributors. And then you have the people that it's their job to be full-time on it, but you don't get there's not this we're not like converting new contributors into maintainers. It's too big of a leap. It's too difficult to just be a part-time contributor with kind of maintainer responsibilities. So what we're doing with the support of CZI is to establish a fellowship or apprenticeship program so we can recruit people from traditionally underrepresented groups in particular and pay them to work full-time on the project while also helping, and while we are paying them to work on the project so that they are committed to it and have the freedom to work on it. Also providing mentorship in some of the other technical or social challenges that make going from a first-time contributor to a maintainer, the challenges that make that harder to get through. So we're really excited to get this program going and are grateful for the support from the CZI Foundation.
I'm personally very interested and excited about the program to increase the the pipeline of contributors, and I think the question of how to turn peripheral contributors into maintainers is really critical. Something that this group is really trying to think about really seriously. Just a comment, not a question.
Yeah, no, and I really I enjoyed the Lara Dabish's the keynote on the first day. That it really spoke to me, so I'm definitely going to follow up with her on her research there.
I don't know if I missed this during the talk, perhaps, but I just wanted to know how Arrow relates to projects like BLOSK, ZAR, other columnar storage implementations in Python.
So I mean, I think there's, I saw Matthias's talk yesterday on ZAR, and I was like, wow, that sounds like a lot of the stuff that we're doing in Arrow, and I think, there's certainly a lot of overlap in the boring bits of what we're doing. We do have a lot of work on efficient file system access and multi-threading and basic IO type things that are really important. If you want to take advantage of your CPU, you got to feed data to it in an efficient way. I'm not as knowledgeable about the specific applications of some of those other libraries, but I get the sense that there are particular features of n-dimensional array analysis that are a little bit different from the kind of other columnar, the type of data that we are mostly concerned with in Arrow. I would guess that you could represent those types of arrays and implement those libraries, those algorithms on top of Arrow memory, and that'd be another way to do it. And that would have the benefits of the the cross-language compatibility and all of those things that I know some of those projects are working towards as well. So, but like I said, I would imagine that there are slightly different focuses that have slightly different priorities. I had a similar thought myself, and there's we've certainly found there's a lot of benefits to working together on a shared foundation, a shared library, and not duplicating efforts as much. But that's like I guess that's the XKCD about creating a new standard. It's now there's another standard. I think it's, from my perspective, in maintaining the R package, it's all upside, because the more people that are using Arrow and contribute something to Arrow, that means that things get better for me in R without my having to do anything, and I like that. So I'd be interested to see ways that we can collaborate in the future.
Cool, thanks.
Hi, I think I got to be next. So yeah, I mean, I'm really interested. I mean, I've actually been talking to Stefan about this. The problem of open source contribution. It's a very rare person actually who is able to sort of join an open source project and really commit to it. I mean, so do you think there's ways that just the sort of fellowship, mentorship, paid model could fail? And if so, how could that work? And is there any way you could?
No, it's impossible to fail. It cannot fail.
Good. That is a huge relief to hear. Yeah.
Yeah. No, I mean, so I think I think the impetus, or like the kernel of the idea for this, was that, first of all, it's we find that people, if they're not full-time able to work on a project like this, it's the only people that I know that can kind of drop in a couple times a month and do something that's not just superficial really, are people that were full-time on it for some amount of time, and they have that context and are able to pick up on it. So the hope with our program was, well, we can support people that are, we can find people that are technically solid, but that would be otherwise be, not have the time, or might be, overwhelmed by the complexity of the project, and that we can give them, kind of cultivate that. And, I think when I'm hiring, for example, there are some people that have a big open source record, and you can go to GitHub and you can see all the stuff they've done. And there's people that don't, and and it doesn't mean that they are less skilled. It just means they haven't had that opportunity, but they don't have that kind of public profile, that portfolio rather. And so I think the goal is to find people that would benefit from having that, would be able to have that, if under the right conditions. The other well, I'll stop there. I think the success is, there are many ways this can be successful, and I think it's worth trying. There are many ways it could be not successful, I guess, too.
All right, thank you so much, folks. We can continue the conversation here on Slack, but I want to move on to the next presenter. And so we have Ben from Dask presenting next. Ben, the stage is yours.
Yeah, so my name's Ben Zaitlin. I'm a Dask maintainer. I work at NVIDIA on the Rapids project, and how Rapids can connect to Dask. Generally, what I'm going to be talking about today is how Dask works in the rest of the PyData ecosystem, with some specific applications to biology. Python is a very powerful language. It's a very powerful tool, and has lots of powerful tools, subprojects within it. Especially in the last 5 years, we've seen kind of explosive growth of Python as a go-to tool for solving any number of problems, but definitely within the scientific community. But it has this kind of problem that it's really great for small or medium data, and its limitation is that it doesn't scale well, or that's often the criticism that Python is met with. And because of that assumption, people have gone off into other languages and other tools to solve that problem. What I want to emphasize today is that we think that problem is largely solved by Dask. So being able to do things that you otherwise wouldn't be able to do with standard libraries like pandas or NumPy, where you might read in some data or do some machine learning with scikit-learn, and things maybe break because you run out of memory, or things aren't going fast enough because it's just running on a single core. Dask can scale those libraries natively. And it really does start off, sorry, I guess I should say that, simply put, Dask is a Python library that does distributed computing, and it scales the PyData stack. It does a bunch of other things as well. It's not just big NumPy or big pandas. You can also build a lot of custom systems. And it's very easy to get started. If you have Anaconda, it's already on your machine. And Dask starts off with, at a starting point of, I have this stack of NumPy and pandas, scikit-learn, or other libraries. How do I make all of those faster? Or how do I make that kind of computation faster? Previous to Dask, people were building maybe distributed array libraries from scratch. There was a lot of really cool HPC projects in Fortran and C++ at large supercomputing institutions. And instead, Dask and the community tries to say, well, we already have these things. Let's just make them, let's just iterate on them in a blockwise fashion. Maybe we can take a chunk of a NumPy array and another chunk of a NumPy array and operate it on multiple cores or multiple machines. So we go from NumPy and pandas, scikit-learn, to Dask array and Dask data frame and Dask ML that maps the API one-to-one as best as we can. Yeah, so Dask not only operates nicely on a local machine, we spend a lot of time thinking about how to make this work on all the major clouds, on new cluster managers like Kubernetes, on legacy systems like Hadoop. It's kind of funny to say legacy system like Hadoop because it's not really that old. And we also spend a lot of time talking to HPC groups as well. So we can work on a wide variety of batch cluster managers. Within maybe as a starting point within what we might call Dask biology, we look at these tools as what I think of as kind of underlying a lot of academic science generally. Dask, NumPy, pandas, PyTorch is becoming pretty popular, and ZAR is definitely a go-to format for a lot of academic groups. Increasingly more within the biology space. And we can assemble these tools to solve very complicated problems. So for example, in computational genomics, where you want to understand maybe genetic differences in humans, the data that they're dealing with is they look at lots of genetic differences within the genome, and they have lots of samples. So I think for the UK Biobank, which is a fairly popular data set, there's maybe 1 million humans, 1 million samples there, around 100 million variable sites within each human. So very quickly, you're at the 100 terabyte level. How do you even approach to start computing on that data? One popular routine that you'll need to run when you study statistical genomics is running an SVD for doing dimensionality reduction. So if you did this with NumPy on the entire data set, this wouldn't work. It'd be great. Actually, many times in Dask pitches, people will talk about, like, if we didn't have these hardware constraints, if we had a machine that had 100 terabytes, we wouldn't need any of these tools. It'd be great if we could just use NumPy or just use pandas without having to go to other fancier tools, but we don't. So Dask makes it as easy as possible to run this kind of computation. And while we're not doing in a simulation of this data set, we didn't do 100 terabytes, you can operate on 20 gigabytes in 2.5 minutes. That's not terrible. It's not the best experience, but at least you can move on with your day. If you got a little fancy, if I put on my NVIDIA hat on, and you kind of threw a bunch of GPUs at this problem with CuPy, you can solve this problem in 15 seconds. that's definitely less time than it takes to make a cup of tea. Maybe it expands the kind of thinking that you're able to, or the kinds of questions that you can ask of that data set when you start pushing towards consuming all of it and not thinking before you even start asking questions of the data, how do I even start computing on it? We're going to kind of follow that thread throughout the rest of this talk. But Dask actually, like kind of some of these other libraries, it's very powerful, but it's not really accessible, especially to domain scientists. What we really need is a layer on top of that. And what I'd like to ask people here is to help us bridge the gap between powerful distributed computing and the tools that you use. So the tools that you might use here, things like Napari, Dask Image, StatGen, X-Ray felt a little weird putting that there, but because so many things layer on top of it as well. But these are the domain level tools that actually, when we've talked to biologists, they're actively using. We want to help connect them to all these very powerful underlying computational tools and data stores. Most of them already are. And I wanted to illustrate what I think, why we want that to happen. Perhaps a lot of you can maybe already see where this is going. So within imaging, we ran some experiments recently, which was a lot of fun, because images are always great. We wanted to run deconvolution. We wanted to deblur an image. So when you read images from a microscope, there maybe is some fuzziness just by the way the optics are produced, and you need to deblur those images before you even start doing any analysis on it. It's a very common task. It's also a lengthy task. So in Dask, you would write it in the following lines. That's not really digestible from for a domain scientist. It's going to be hard to convince microscopists to write this kind of code. It also doesn't do anything right now. It produces images is going to be a distributed array. So what we first need to do is connect it up to something like Napari. We actually need to visualize it. And we can do that. And we're talking with Napari folks about how to make this better. But maybe the abstractions that we want are things that look like the following. We do some imports, but load images, deconvolve this thing maybe is an abstraction that that microscopists understand or other image scientists, and then use Napari to view all those images. And we can do that, but what we want to do is do it in real time. So the last experiment that we ran with this was on a 16 gigabyte Z stack, and it took 30 seconds with 16 GPUs. That's really great. It's like down from tens of minutes or maybe even hours. But what we are pushing really hard towards is doing this in a real-time setting. We want to move part of this conversation amongst domain scientists towards not how do we solve the problems that they're currently working on faster, and we definitely want to help with that, but we also want to expand the thinking of rejecting the assumptions of computational realities. Can you ask bigger, broader questions? We've seen this success in the past with the Pangeo community. Many people of that community are here. They have very similar problems. Their data comes as images or readings from various sensors. They have a lot of it. They have medium amount of it. They work with collaborators throughout many institutions and many nationalities. And they took this same kind of core stack of Dask and NumPy and Pandas to accelerate those workloads. And they've built their own custom tooling on top of it. And we want those same things to happen for biologists, for domain scientists within the biospace. With a grant from CZI, we've hired developers that, I think they're called like pie-shaped developers. They're very deep in two areas. They're deep computationally, but they also know how to speak biology. They're domain specialists themselves. So we need to bridge this gap between the Dask community, the accelerated computing worlds, and to people that are actually doing science and finding the right abstractions and the right matching for how to do their science in a way that is seamless, but also accelerated. I think I'm close to time, but maybe I'll just wrap.
1 or 2 minutes.
Okay. So our mission is to scale science. That's what I'm trying to do within NVIDIA. That's what Dask as a whole is trying to do for academic groups. The software community within Dask is fairly extensive. We have lots of contributors. We have institutional support. We have a nice grant from CZI to go after these problems. You can read more about it at dask.org. Thanks.
So really great talk. So I'm one of the project leads for the Chime 2 project. And so what we're interested in doing is kind of the same thing you guys are doing here in your goal of like mapping these high performance tools into something that domain scientists can use. And Dask is actually something I've been looking at a lot for use in Chime 2. And so one of the things I was curious about was, how does Dask, is there like a convenient way to map Dask onto like a queue system? So something like Slurm, because that's kind of a typical environment for our users. And it'd be really cool to run like a scikit-learn model across, you know, a job submission system. This would be like a really quick way to just make what we already do way better. So I was wondering kind of what was out there for that.
Yeah, there's a project called Dask Job Queue, which works with all the major queuing systems. We've actually had a lot of success working in job queue places because Dask is fault tolerant, like Spark or other things, but queuing systems will often prioritize things in a way that's we can take advantage of. For example, we can say, give us, you know, you can exist on the queues that will maybe disappear after a few minutes. And those things aren't like well utilized, but Dask can take advantage of that and dynamically spin up and spin down workers.
Does it require still kind of a central process to keep track of all of those different workers?
Yes, there is a centralized scheduler in Dask.
Okay.
So typically that is either run on an edge node or on a, you launch that separately onto a queue that is more stable. But yeah, in general, like you can launch machine learning jobs with Dask on PBS, on Slurm, on Moab.
Really great talk. Dario said I could jump in. I'm wondering, Benjamin, the example that you gave of the UK Biobank, sort of doing an atomic operation on it, is that something people are actually working on?
Yeah.
SVD of the variant store.
I think that there's a group, Related Sciences, Jeff Hammerbacher's group maybe is doing UK Biobank GWAS studies. I think I have that correct. I would go, look for GitHub and Related Sciences to find out more about that.
Okay, thank you.
If you interact with PyStatGen, I think that they're a pretty welcoming group.
Hi, thanks for the great talk. And so I have a kind of issue maybe. So we're developing Elastic and we're doing exactly that you was talking about. So we're trying to bring these computational tools directly to the scientists. But in our exact use case, interactive labeling and model training, we really want to use Dask as a backend because our kind of custom built backend is not that good, obviously. But the problem we have is that our images could be like maybe 3D and maybe 1 terabyte large at the high end, and they we want to process them lazily. So we usually focus on like a very small chunk, and then people start doing something with that. And we'd love to use Dask for that, but the problem we have is that you need to you need these chunks to be very, very small. And also chunks need to overlap because we're computing some image filters on that. And in Dask, unfortunately, because you need to create the whole graph in advance, it's very slow because you need to compute all the overlaps and all that stuff. So what do you think we can do for that and still use Dask somehow?
Yeah, so you would have to, I don't know offhand. What I would recommend you do is actually raise this issue on the Dask image GitHub issue tracker and describe your workflow. If you're having problems generating if your issue is that you're bottlenecked by the scheduler creating the graph because you have so many chunks that it's taking a long time to generate the graph, there's a effort between NVIDIA Cap One and the Dask community and Coiled to improve the scheduler significantly. If your issue is just with actually doing the map overlap calls, perhaps there are more efficient ways of chunking your data and making it larger. So maybe just getting a bigger machine. We need to dig into that, I think, a little bit more. And the Dask image community is looking for more workflows, so I would be vocal there.
Yeah, thanks.
We'll need to move forward with the next talk. So round of applause virtually for Ben and his talk. And next up, we have Vincent presenting on Bioconductor build system.
Really big thanks to the previous two speakers for, I hate to say it this way, but sort of cutting me down to size. I mean, those are just tremendous resources and performance concepts to think about. So I'm really grateful to have the chance to speak here. I use the phrase community emulation in conjunction with this build system, and I hope that I can make sense of that concept, if it isn't already humdrum to many of you. So the build system that we're talking about here is life support for a software ecosystem. And it has to address objectives of users, and it has to coordinate and really be valuable to developers. So the users want to use the ecosystem to develop scientific wisdom and to use the best tools available to answer the questions that they have. The developers want to avoid reinventing the wheel and want to use the most efficient tools available to produce procedures that the users will actually like. So the build system has to address these issues somehow. And it also defines a cadence by which new things become available and things are tested and reported on so that people can fix them or make them better. In conjunction with all of this, the build system should be able to provide measures of, let's say, frequency of failure of build tasks, aspects of maintainability, complexity of code, and so forth, that will help developers improve the code base. And we're going to talk about a build system for the Bioconductor project, and the build system that's currently functioning is the work of Hervé Page at Fred Hutch. And it's really the brainchild of Robert Gentleman, who's one of the two people who created the R language for data science. And Bioconductor is a kind of vision for reproducible data science on genomes. And it's a community that shares this vision and helps to build it out. And this is a little schema which I try to explain why students would want to learn about Bioconductor when their main concerns are basic genome biology, let's say running assays and specific experiments and trying to interpret them. As we think about this more broadly, we see that the genome biology flows through biotechnological innovation, ultimately generating lots of high-dimensional data, and we need to do all kinds of things here. And then if we want to ultimately come up with personalized genomic medicine, we've got to move up through systems and network biology, also through population genetics and genomics. And for 20 years, Bioconductor has been sort of in the middle, dealing with new biotechnological innovations all the way back to cDNA microarrays up to single-cell sequencing. Doesn't cover every sort of thing, not much in imaging at the moment, but some. And dealing with issues of ingestion of data, throwing the data through quality control, data analysis, annotation, reference genomes, and so forth. So Bioconductor does all these sorts of things in an open way, trying to build a developer community and a user community that are symbiotic and take care of things so that people can move in the direction they want to move in genome science. And my claim is that the build system is really there to emulate the community. So anything interesting that a user or developer would like to try, multiple independently developed packages, a language, and a tool set that's evolving. And the concept of the workspace that a Bioconductor user has is one in which they're sitting, interacting with the data, and packages and data are found, ingested, new packages are loaded in, they're graphed, they're combined as they like. And the Bioconductor packages are designed so that pedagogic guidance is built in. So there's a vignette that has to be a part of your Bioconductor package that gets computed every time the package is installed and every time the build system runs. Not only do we have vignettes and workflows, but we have books, and I'll show you some examples of that survey large topics and constitute very large-scale integration tests. And the idea of the build system is that anything that a user or developer could want to do should be tested on a daily basis. So this is a view of the check results node of our main website, and it shows that integration is tested at various scales. There are packages, workflows, books. It's done on 3 platforms, and the cadence is that R is going to change fairly frequently. It used to change every 6 months with a major dot release. But more than that, biotechnology is innovating all the time, so we need to do a new version every 6 months. And in the develop branch, we can have breaking changes and figure out what they do, but in the release branch, which we expect most users to be relying on, there are no new features introduced, only bug fixes are allowed. And this is what the check report looks like. You can see that for 2,000 Bioconductor packages currently in the software branch, you need to install 3,900 packages. This includes CRAN dependencies of all of the 2,000 Bioconductor packages. So there's really quite a lot of software needed to do this. And if you drill into the build report, you find that every package gets a certain panel here. And when there are errors on certain platforms, you can click on that and then find that here's a nice package for differentially expressed regions, which failed because another package called NIT citations could not be installed. And that is a temporary gap in citation for bibliographies that causes package failure for a really biologically oriented package. So it's a very interesting interplay between different components of infrastructure that can lead to errors here. And this is something we know about, and we can substitute in a working version of this package if we need to. But the system wants to be agnostic and just take things from CRAN and so forth that are available to the entire community in order for this process to be most emulative of the community itself. So in summary, we got 2,000 Bioconductor software packages in 2 streams, release and develop, 3 platforms, and all the necessary system dependencies and so forth have to be managed. This build system is manageable, but there's a fair amount of human intervention on a regular basis. And there's been lots of new technologies in the past couple of years. Docker is becoming much more prominent. GitHub Actions are relatively new. And other services like binary package management by rstudio.com are new opportunities. Our project doesn't have an FTE for DevOps, so core developer time is spent on the build system. We want the developers to be working on the biological problems, infrastructure and so forth, not the build system. And so it would be nice to offload effort to the contributors, have the stuff that's coming in be very reliable at the start, so that the build system just really relies on, just really performs, let's say, distribution and not a lot of diagnosis. Now, I mentioned books as a part of the Bioconductor ecosystem, and here's an example of the build report for books. Unfortunately, in this track, we have a number of errors. But the one that succeeded here is easy to get to. It's for single-cell biology, and it has a bunch of chapters. And every time the build system goes through the book, every example, every visualization, and so forth is computed. And this idea of executable documentation for community emulation, I think, is critical. For the single-R book, you have 125 packages involved. And for this orchestrating single-cell analysis book, every chapter of the book, and there are about 50 of them, has a similar software stack of order a couple of hundred packages in play. And the build task is every computation, every package load, and every visualization is repeated at each build for each platform. Here's an example from the single cell book on dimensionality reduction, where we're looking at whether there could be a batch effect that's important for some of the inferences that are involved. So this book idea, I think, is important in thinking about this community emulation idea. There's also the question of how do packages come into the ecosystem? And then we have another piece of software, the single package builder, developed by Laurie Kern over at the Roswell Park Cancer Center. And we have a review process, which is, again, very human intensive to get packages to a point where they can go into the build system and be used by the community in a reliable way. And so the CZI project helped us think about how to upgrade this build process. There's a nice package down site, BioC build tools, which defines this, includes a Docker file and a Docker Hub image. And what I want to show you is an app that's developer targeted that works for a family of packages. This is what the package build site looks like, a package down site looks like, gives you all of the aims of this project. And then I'm not going to demonstrate this in real time, but this is how a function in BioC build tools helps developers, in this case, the developer of the BioC file cache package, think about the reliability of their tool at this time. So there's a bunch of tabs. Here's the note tab. When you run r-command check on a package, it gives you some notes about some issues. There's also something called BioC check, which is a somewhat more stringent collection of tests. For example, 80% of manual pages should have runnable examples, but for this package, they don't. And then there are these notes about style. Package coverage, test coverage of different files is also computed. And the interdependencies of different packages can be shown graphically. And this is iGraph, thank you very much, through a package called VisNetwork that shows us the different dependencies of BioC file cache. Very interesting for developers is the function interdependence, and this is another thing produced by this PackageNet package. The pink and green tell you about the test coverage of the different packages. When we drill down, we can blow up that graph and find the names of the different functions that are involved and whether or not they've been tested. And then we can think about whether this sort of design is what we really want, or should we start to simplify the interdependencies of the different functions. As a longer term goal here, it'd be very nice to understand aspects of resource consumption during the build process for the ecosystem or for a family of packages. And this is something from a package called rcollectl that works only on Linux at the moment to figure out how much of your CPU is being consumed, how much is flowing over the network, how much disk you're writing, and so forth. And so in summary, I claim that community emulation is a meaningful goal that an ecosystem build framework can aim for. And for Bioconductor, packages and workflows and books are different scaled collections of code, explanatory text, and visualizations that emulate all kinds of things that will go on as the community makes use of the ecosystem or contributes to the ecosystem. And so the BioC build tools that the EOSS project has supported have now a package down side, and a container, and all the references are in the slide set that introduces new facilities for metrics and functions and tests and interrelationships so that we can add to the reliability and durability of the ecosystem. So with that, I'll just acknowledge the different grants that underlie this work, Bioconductor and the BioC build tools, and I'll thank you very much. Any questions?
Maybe I'm gonna just make this comment to kick this off. Super interesting, the book development and how it's being growing, also the challenges of maintaining this like accurate, up to date, and usable. I just want to make a comment and make sure that you're aware of a similar effort that the Carpentries is working on with the Carpentries Lab initiative. They've been building like a repository of high quality computational curricula, like capping many of these packages and tools. And they're really trying to figure out a scalable model for maintenance and peer review and it's like quality assurance, which is one of the big problems I guess that everybody's facing. Just to make sure that you're aware of the project. And
right. Yeah, we are getting closer to the Carpentries. We have a number of people that are working with them. So yes, I mean, I didn't mention it because I think it's still somewhat, it's very new. It's probably just the past 3 months.
Yeah.
But yeah, we're there, and if we can help with that aspect of it, that would be great. I'd rather get help from somebody else.
Right. Yeah, they're still in this staging phase, but they're getting some good traction.
Great.
Yeah, sure. I was just going to ask, sort of looking around, so surveying the other languages, Julia and Python and so on. Is there anything that you really wish you had that you don't have?
Oh, well, I would say what I wish is awareness, because we do have a very nice interface to Python called Basilisk in Bioconductor that really helps ensure that you have a consistent set of Python packages at the version level, so that you don't cross incompatible versions of different packages coming from different environments. So I think we've worked hard to get reliable interoperation with Python. That hasn't been explored by too many people in different packages, but there's some. With Julia, same sort of thing. I know there are Julia interfaces. I don't know how much functionality that's key for Bioconductor users we'd like to bring into the system. But it's really the awareness. It's the killer example that says, oh, I need to be able to do that. I don't want to write it myself. Let me try to incorporate that. And I think R has been very favorable towards that. And I hope that answers your question.
So I just wanted to ask if you have used any of the stuff coming out of the Valid R group that have been doing sort of a set of additional package diagnostics that the R consortium has been funding for primarily pharmaceutical, but essentially for similar, having a set of general package diagnostics and a tool to provide sort of a score sheet. And they've been developing sort of things similar along these lines of sort of the dependency mapping as a method of looking at, sort of package fragility.
Very nice. No, unaware of it. We'll jot it down, and I thank you.
All right, thank you, folks. And Sumana, the stage is yours.
I'm Sumana, and I work with Python packaging, and I appreciate your work in science, because if you've ever run pip install, we serve you, and you're playing on hard mode, because Python packaging for scientific software often involves just using all the possible edge cases, and we have we know that it's difficult, and we're trying to make things easier. I'm now going to try and show a video.
There's a big change coming to pip in October. It'll be a great foundation for making it easier to deal with installing packages with Python.
Computers need to know the right order to install this stuff. To install X, you need to install Y first.
So, when Python programmers share software, like when they publish packages in PyPI, they have to precisely describe those installation prerequisites.
And then pip needs to navigate tricky situations when it gets conflicting instructions.
Up until now, pip's been very inconsistent in handling this stuff, which makes it easy for a Python environment to get messed up.
So we've been adding a proper dependency resolver to pip, so it's better at handling that tricky logic and easier for you to use and troubleshoot.
We're testing it in beta right now, and in pip 20.3, coming in October, the new behavior will be the default.
Once you're using the new resolver, pip is going to be stricter and more consistent. So things won't mysteriously break as much, and new features can be added that lots of people want.
But some people and some packages are going to run into problems in October because the transition to a stricter approach will break some workarounds that depend on inconsistencies.
We really want this change to go as smoothly as possible for you and for our bug tracker.
So now's a good time for you to visit our migration guide at the link below and try the beta of the new resolver. There's a link there for you to report feedback, good and bad.
The other link is to sign up for our user experience studies. If you sign up, then we can get your opinions in the future with surveys and interviews to help make Python packaging better.
No matter whether you use Python every day or not, whether you're an open source software maintainer or an open source software user, please sign up because your opinion matters.
I'm Nicole, and I work on user experience for pip and Python packaging.
I'm Pratyot, and I'm a pip maintainer.
I'm Bernard, and I work on the user experience of pip.
I'm Sumana, and I'm the project manager for pip.
I'm Paul, and I'm a pip maintainer.
I'm Ziping, and I'm a contributor to pip.
I'm Georgia, and I work on pip's user experience.
I'm Ernest, and I work on the Python packaging infrastructure.
We're some of the people who will read your bug reports and your compliments. We look forward to hearing from you. So that was basically a 2-minute YouTube video we made for the general public to let them know about what was coming. To remind those of you who possibly don't use that much Python, pip is a tool to download and install software onto a user's computer. Often that software comes from, for instance, the Python package index out in the cloud. Sometimes it comes from elsewhere, but it ends up being an incredibly widely used utility, including by people who aren't programmers and do very, very little with software. So we asked for and got some money from CZI and from Mozilla Open Source Support to do some pip resolver and user experience work in 2020. We needed to finish our work overhauling the dependency resolver within pip to make it stricter and more robust. And this could have been a catastrophe. And I think it wasn't. And I'll get to more on that later. We also needed to make our maintainership more sustainable so that we didn't just have the same few people, mostly unpaid, trying to get this done. We wanted to improve the user experience even on the command line. Yes, it is possible to improve command line user experience. And we wanted to improve the design skills in user experience of the Python packaging maintainer world, not just pip, but people who worked on all these different related tools. So here's the major things that changed in the resolver, since that's going to be the thing that affects most of the people here. We have reduced inconsistency. So pip will no longer install a combination of packages that's mutually inconsistent. And it's going to be stricter. So if you ask pip to install 2 packages with incompatible requirements, it will refuse. If you've been using workarounds to force pip to deal with incompatible or inconsistent requirements combinations, now's a great time to fix that. We knew that a lot of organizations out there were using inconsistent dependencies. They've been used to it because for years it was possible. And sometimes they just didn't realize that it was going to be a problem. Sometimes they were actively trying to fix a problem that we were now obviating with the new resolver. They did not realize that their environments were built on Jenga towers. So we needed to address that. So the new resolver is out. It's in pip 20.3, which we just released a couple of weeks ago. So I'm going to give you an example of the new pip resolver where the legacy resolver misbehaves and the new resolver behaves properly. So here we have, I've set up a virtual environment and I'm using the deprecated legacy resolver to try to install these 2 packages using some requirement specifiers that you might have seen things like in the past. I hit enter and it tries to do some things and then it says, well, just so you know, Flake 8262 requires one of these versions of PyCode style. You're going to have this, which is incompatible. So it installed it in about 2 seconds, but it knows that it did something that very likely will lead to some problems down the road. Here, I'm using the new pip resolver, and I'm asking, okay, do that exact same thing. It takes a little less time, 1.87 seconds, and it installs PyCode style 2.0.0, which is much preferable. There's no incompatibility. It just had to do a little bit more thinking to figure out what to install. Here's another example. And I want to mention, by the way, that it can be difficult to give you good demos because many of the changes that are most impressive on complicated problems where pip has to download and install a lot of stuff, that can be slow. We only have 15 minutes. And the new resolver is stricter. So we've incentivized many Python package maintainers to clean up their dependency chains so pip installs work properly. And this means some of our demos don't work anymore, which is good. But it's sometimes the worth of the demo, right? You miss that. So with the old resolver, Pyrax installing this would error out with a wall of text. Now it errors out with a more informative wall of text. So that's nice. Here's the more informative wall of text. I'm pointing to things because it's real hard to see. Yeah, I'll show you what it. Here is the kind of helpful output we now give. It tells you, hey, pip is now looking at multiple versions of this package. And if we're trying to determine what's compatible, this is taking longer than usual. You might need to provide the dependency resolver with stricter constraints. Here's what you could do. Or in another situation, we'll tell you, hey, this dependency conflict is caused by these two things. And here are some things you could do. This is an error called resolution impossible. And you could help visit this particular documentation page, which we made just for this situation. I should also mention, we know that this output does not look great, and we would like to fix that. That is the next chunk of work to do. But our user experience experts help us so much in developing these improved error messages that acknowledge user pain and then tell them, hey, we know this hurts. Here's something you could do. So we know that we probably changed a lot, and we may have broken stuff for a bunch of you. I've put a link to this page of the documentation into Slack and into Zoom. But yeah, pip is only considering the packages you're installing in that command. This is the only kind of promise that we can keep right now. And we're changing our support for constraints files, editable installs, related functionality. Hash checking mode requires that all requirements are specified as an equals mesh. Links are not allowed as constraints. Constraints cannot have extras. All this stuff, it's worth looking at if you think you do anything even mildly interesting right now with your requirements.txt files and things like that. Also, pip 20.3 users who are using Python 2 are still going to use the legacy resolver by default. Python 2 users should upgrade to Python 3 as soon as possible, since in pip 21.0 in January 2021, pip is going to drop support for Python 2 altogether. So these are things to look into, and Pradyan is here at the convening today, and we're also available to talk to you in general in case you need help figuring out how this affects you. Let's talk a little bit about the colleagues who are here. So I mentioned Pradyan just now. I also want to give a shout out to Georgia Bullen and Bernard Tyers, who did a bunch of user experience testing and research. Also Nicole, who you saw in the video, did some of that as well. I wish that Paul and Su Ping could be here, who also worked on the development side. We had a cast of thousands here, right? Thank you very much. And Georgia, Bernard, Pradyan, and I are available to talk today during the convening. We needed to have a gradual rollout on this. Our transition timeline for something that affects practically everyone who uses Python needed to be gradual. So as soon as we found out and could announce that we got the funding, we told people in December 2019, hey, this is coming. When we released pip 20.1 in April, we also announced, hey, there's an alpha version of the new resolver available, opt-in, using the optional flag such and so, but pip still defaulted to legacy behavior. So we were shouting, hey, this is going to be coming in March. And then we put out a push, hey, people, please help us test the alpha in April. Then in July, we did a bigger push. And we said, look, there's a beta of the new resolver available. Opt in. If you install pip 20.2, use such and such a flag. Pip still defaults to legacy behavior, but please help us test this. And through April, and then especially through July, August, September, October, and even early November, we were getting bug reports every week from people who were doing this testing that we heard about us. Now in November, just a few weeks ago, we rolled out PIP 20.3. PIP defaults to the new resolver. A user can opt out and temporarily choose the old resolver behavior using a certain flag. Again, thank you so much to our user experience people who helped us figure out what the names for those flags should be to improve usability. Our current plan is that PIP 21.0, scheduled to come out in January 2021, will use the new resolver by default still, and the old resolver will be no longer available. We are still going to double check that just in case it turns out that some users really need that legacy behavior for longer. I want to point out, in our original plan, we thought that new resolver's default would have happened in July. We delayed that. We thought it wasn't ready. And I really appreciate the forbearance of our funders and the Python world in not pushing us to release something before it was ready. I think that's one of the huge things we did. We also used our prerogative to delay our scheduled release from October to November for a variety of reasons, including making sure we weren't disrupting data science efforts around the US election in case of massive violence, which thank goodness did not actually happen. But we wanted the whole time to make sure there was always a way to go back to the old behavior for as long as possible, and that we only released this with the new resolver's default once we felt confident that it was right, that it was production ready. How did we get the word out about this? Well, here's an example. We put out blog posts as early as you can see here as late 2019, but also in March on the Python Software Foundation blog and various other places. We knew there was always going to be a non-zero number of people using this who don't really pay attention to infrastructure that they depend on unless and until it breaks. But we always want to mitigate that and learn about how we can inform and incentivize those folks in the future. I think of it as like if you work for a city and you're changing the collection schedule for garbage pickup, sanitation, then you try, right? You try to send out flyers and stuff like that ahead of time because they're your neighbors and you want them to feel up to date, even if you usually don't pay attention to that kind of stuff until you need to. Here's some of how we did this, and we learned some of this from previous funded efforts. We put a message in pip output saying, hey, heads up, coming up, you might experience errors, try the beta. We sent emails to sponsors of PyCon, the PSF, and PyPI saying, hey, tell your engineering departments these changes are coming. We went on podcasts, we tweeted, and so on. There's a bunch of this in the links that I shared. I also want to thank so much our user experience folks for the surveys and research they did. Bernard, for instance, helped us figure out what people wanted in the resolution impossible error messaging, helped us develop better backtracking docs. Here are examples of, through the interviews, through the surveys, what people got, what we were able to get so that we could improve what we made and how we messaged about it. So what's next? We're doing some user experience training for packaging tools maintainers. We need to figure out when we're going to rip out the legacy resolver. We could work on some great features like pip upgrade --all to upgrade all the packages in a particular environment, better support for reproducible environments. We're out of money. We no longer have any funding to do any work like this. Here's a link in case your institution wants to help with that. We'll also, of course, be talking with CZI to ask for that. And we want to thank you. Thanks to CZI and Mozilla. Here are some links to contact us further. And we have a few moments for questions.
Yeah, thank you so much, Sumana. That was a great presentation and a tremendous amount of work. And so my question just relates to, and let me know if this is too in the weeds, but spatial packages and libraries. So I do a lot of teaching and I have a website where I've got people from all over the world coming and working through my lessons, and installing packages is like one of the biggest headaches because the students get stuck and then their learning stops immediately. And then Python's a terrible thing because they can't get to the code. It's not terrible. But anyways, I was just curious if there's been any testing with some of the spatial libraries, because we've had to move away from Conda towards Conda because of that. But everyone knows pip. And so I'd prefer to use pip and it's fast. So I just was curious if any work was being done in that space or if you had any thoughts on that.
Right, right. So first off, hey, my sympathies. Python packaging has a lot of pain in it, and that's not great. I'm not a fan of that myself, which is one reason why I hope that you could share with the rest of your colleagues and students the user experience surveys so that they can sign up and talk to us a little bit more about the pain they've been experiencing. The more systematic information that we have and can collect about these things, the more we can show that then to funders, for instance, and say, hey, give us money to solve these problems. And the more that our maintainers can make better choices and say, oh, okay, this is a use case that has, we thought maybe was just an edge thing, but there's a lot of people running into that. Let's accommodate that. Another thing I want to mention is we want to stay available to you and to anybody else who wants to talk with us about the specific pain that you're having. I see there's already been some Zoom conversation in the chat about how to move forward specifically on GDAL and some other related stuff. But I also want to say, I don't think that it's necessarily bad for us to have a few different products or workflows in this space. I think that I haven't done enough systematic study, and I think we need funding to make this kind of systematic study, but I think it's very likely that there is a place in scientific and numerical computing for a pip-centric workflow. There's a place for a workflow where you're doing things through your package manager that comes with your Linux distribution. There's a place where you use SPAC, right? Maybe if you're doing high performance stuff. There's a place where you use Conda. I think it would be great to have some proper product management conversations among all these parties to kind of divide things up. That's my personal opinion. I'm not speaking on behalf of the PSF.
I think just one other comment to that, I really thank you for that. And I love that idea because, as a scientist, we tend to want to just work on the science. We don't want to get stuck with environment setups. So if there was some coordination across channels and package managers, this is how you do spatial stuff, this is how you do, or if there was any coordination or guidance, it would be really helpful because it's such a pain point for teachers and then students and scientists.
Yeah, that's exactly. You are one of the groups we don't want to hurt, and that's one reason why we've been trying to spread the word as much as possible. Please take these user experience studies so that we have enough data to help us make the next step. Dario, I'm just going to jump on one question I see from the chat. Do you have suggestions for pip installable Python packages that are still running Python 2? Will pip install break completely next month? If you stay with Python 20.3, then it will continue using Python 2. I would really deeply ask you, please see what you can do to migrate to Python 3, not just for you, but for other dependencies that in any way depend on you, right? Like we are an ecology together. And I think we have decided, right? We need to break off of our Python 2 support so that we can move forward and have less, fewer things to maintain. So you will not be able to upgrade to pip 21.0 if you're using Python 2. So yeah, you can stay with Python 20.3 and continue to use Python 2 for some time. But as you probably know, you will encounter more and more problems like this as the rest of the ecosystem starts to fall away from you. I'm sorry, I don't mean to sound punitive, but this is the fact of the matter. Right.
You said that there was a bunch of this was obviously a major project with some potential pitfalls. I was wondering if there was any challenges that you didn't anticipate or things that were easier that you thought would be majorly challenging.
I would say that I personally came into this knowing, oh, okay, we're going to have a lot of edge cases. We're going to have a lot of things that we need to deal with. I think only in the process of developing the new resolver did we really end up documenting so much of what pip had been used to do, what power users had been using it to do. That list in the here's all these things that changed because we no longer support them. Some of them were things that we didn't even realize people were doing, these different combinations of ways to try to tell pip what to do. So, and Pradyan could probably speak even more to that. So I think that was that kind of combinations and permutation stuff was a reason why we ended up pushing the release from July to November, right? Was covering a bunch of this stuff. I also want to mention, I wish that if I could go back in time, one of the things I would do is I would have tried to allocate more time and more resources to trying to do get resources for automated testing. The fact that Travis CI for us takes 30 minutes to run anytime we want to run something, it has been a huge blocker for us. So if we'd had more cloud resources to run matrixed testing and to be able to do the, oh, come on, just do this thing that people tell us to do, which is grab a bunch of requirements.txt files off GitHub and then run those just to see what problems shake out. Well, okay, that would be nice to do if we had a zillion CI compute cycles available to us, but we don't. So that's something that I would have put a little bit more resources into trying to shake out.
And I want to welcome on stage Sean and Matt from the EOSS project.
Thanks, everybody. So we're going to talk to you today. Sean Goggins and myself, Matt Germanprey, are going to talk to you about the EOSS project. And our project is maybe a little bit different than what we've been talking about so far in this session, is that we're an open source project that is aimed at helping you reflect on the people and the projects that constitute your community. So it's thinking about the community health for your own projects or the projects that are around yours. So I'll give you a little bit of background on the EOSS project and kind of what our philosophy is, and then turn it over to Sean to talk about one particular piece of software, a critical piece of software within the EOSS project called Augur. So the EOSS community, we were formed in 2017. We're a project at the Linux Foundation. We were started with support from the Alfred P. Sloan Foundation. Our goal is to make community health more transparent and actionable for others. We could maybe talk for a long time as to what community health means. I think it means a lot of different things to a lot of different people, and that's all right. So the project itself is really set up around three different kind of areas. So the first is metrics. So we do develop metrics around community health, and those metrics are set up around a variety of different focus areas: evolution, diversity and inclusion, risk, value, and common metrics that are kind of common across to all. So we develop metrics that provide transparency and actionability, say around risk, or provide transparency around value for your projects. We do bring a number of these metrics forward through some EOSS initiatives, and I'll talk about these just a little bit. So we have an initiative called Diversity and Inclusion Event Badging. We have EOSS community health reports, and we're starting to build initiatives around dependencies. There seems to be a lot of talk about dependencies, not only in this community, but also in the commercial communities as well. So dependencies are critically important. We're talking about initiatives there that can provide support for people. And then the EOSS project is also built through three different pieces of software. Augur, again, who Sean will be talking about Augur here in just a little bit, Grimoire Lab, and Cregit. Hello, Sean. And so the EOSS community, when we develop our metrics, this is kind of philosophy here. So I'm not going to get into the real details of how we work as a community, but we're agnostic on the metrics in practice, meaning that we don't ascribe value to particular metrics such that, issue response time being high is a bad thing, or pull request length is a good thing. So we don't ascribe value because we know that metrics mean different things in different contexts, and we're working to work with groups to identify what those contexts are and make the metrics meaningful in those specific contexts. We don't build metrics just for metrics' sake. We tried this at the beginning, and it didn't work real well. So we're considerably more systematic in how we develop metrics. First, by defining the goals that we're trying to obtain, and only through those goals can we ultimately build metrics that help inform those goals. And you can check out this link here for the latest release of metrics around those groups that I mentioned earlier: evolution, D&I, risk, and value. And again, our goal is to improve transparency on community health for your own projects or projects that you may have an interest in. So these could be upstream projects, these could be downstream projects, these could be projects localized to you. And as we talked about yesterday with Karthik and James' talk, projects that constitute an ecosystem, whatever that might mean. I have to figure that out. And again, when we provide that transparency, it's around transparency on risk that might be associated with your project, or it's around transparency that's associated with value as ascribed to your project. So what are the metrics and what are the ways that we can think about these things as relevant to your project? So within the project, yeah, we know metrics can be gamed. We've been thinking about this quite a bit. We also know that metrics can be completely overwhelming. So the amount of trace data and questions that people have against their communities can be completely overwhelming with the data that comes in. And we're also pretty aware that metrics can uninspiringly tell you that you're doing less than horrible. So sometimes the metrics don't always tell you that you're doing great. They just kind of tell you that you're not doing so poorly. So around the gaming issues, we have developed a very nice group of people to think about what the goals are that these metrics are aiming to hit, thinking about ways that we can address issues of gaming. In terms of overwhelmingness, we do have efforts here. So for example, highlighting anomalies around metrics, right? So not just the metrics themselves, but where are we seeing abnormalities to kind of filter through the overwhelming amount of data that can come from metrics sometimes. And then trying to use metrics as inspiration. We're working through this one and thoughts are extremely welcome on this. So overall, the goal of the CHAOSS project is to highlight the good work that you're doing and highlight the good work that's occurring in the projects that you care about, and also locate you as project maintainers and project contributors to areas that might need more investigation. So why are our pull requests taking so long to close? Why are our issues staying open so long? I'm just kind of picking high level issues here, but locate you in areas that might need more investigation by yourself. And these are context specific investigations. So from all this work, we have a couple initiatives that I'd just like to highlight. One is diversity and inclusion event badging. So we have taken the CHAOSS D&I metrics and put them forward as a badging project. So if you have a virtual or in-person event, you can actually participate in this initiative to receive a badge for your event for attending to D&I issues. We actually follow the model from JOSS, the Journal of Open Source Software, so that the application and reviews are done all in the open and on GitHub. So we ask questions about speaker demographics, how you're documenting that. We ask questions about attendee demographics, codes of conduct for in-person events, things like family friendliness or diversity access tickets. So I encourage you, if you have a virtual event, to take a look at that. Again, putting our metrics into practice. We also provide community health reports at a fairly high level, free for communities. So this is an example community health report right here. We do it one repo at a time. So if you're going to do a community health report, maybe pick a couple repos that you might do a couple requests, or just pick one big repository. We do this for Git and GitHub. And so as part of the community health reports, again, we're doing these initiatives that bring the metrics to practice that could inform people, and also utilize the software that's part of the CHAOSS project. And one of those pieces of software that helps generate the report that you're seeing here, critical pieces, is the Augur piece of software. And I'm going to turn it over to Sean to talk very specifically about this CHAOSS piece of software called Augur. So Sean?
Yeah, go ahead, slide. So I want to point you, first of all, building on Matt's last slide about the community reports, to this red underlined link in the middle. Those are Jupyter notebooks that we've used to build community reports in more detail off of a series of the tables that we have, which I'll explain in a minute. And we can generate some really nice visualizations about what kinds of new contributors you have, what times, how often do you have second-time contributors, what is your volume and life cycle, what is your response to pull requests in contrast to other communities. A lot of information slide. So I want to drop back conceptually here and point out that when we do the tooling, fundamentally all open source projects, scientific or otherwise, are centered on a repository at the beginning, at least. And what Augur does is it collects data about the commits, the change requests, which GitHub calls pull requests, issues, messages related to issues, pull requests, and commits, software dependencies, and then, of course, derived from all that information, we have awareness of who the individual contributors are. Slide. And all of that data, so there's repo and then there's these basic things. We have a complex relational schema through which we use data collection workers, which are on the right and a little bit small on my screen right now. Machine learning workers, which generate insight, and push notification workers right now, which pushes notifications of anomalies or just metric reports or comparisons out to a Slack channel that you can subscribe to with Augur. Slide. But I want to come back to this conceptual component of the Git repository really being in the middle of the tooling that we generate, and all that information about the Git repository and this notion of an individual contributor. Slide. But really what's happening is we have a network of individual contributors who are all participating in a repository and also possibly participating in some of the repositories upon which I depend. So Python pandas, for example, I can tell you we depend on that. So inside of Chaos, when we're looking at a repository, we have a lot of granular data. But when we're thinking about an ecosystem, so some of the ecosystems we've looked at involve as many as 7,000 different repositories, we zoom way out. Slide. And so we have this giant universe of individual contributors contributing to some matrix of repositories. And we can find these little dependency clusters where I have people contributing, similar groups of people contributing to repositories with mutual dependencies. And so there are varying degrees of this that we encounter when we're actually analyzing the data. And but the important thing to understand is that with the granular data that we have, you're able to zoom out and kind of get a picture of your ecosystem and sort of a sense of where those pieces of the ecosystem cluster. All right, so the next thing that we can do is health patterns. So we can find patterns using our machine learning workers that group projects in whatever you'd bound as an ecosystem. Typically it's 100 repositories or more, gives you enough data to start to cluster things in useful ways. And these ecosystems, these patterns that we can identify revolve around the behavior and actions of contributors into repositories. And again, all of this builds up from metrics that are focused on the essential forms of contribution to an open source community: commits, change requests, issues, communication, people, and dependencies. And so we build this ecosystem level metric pattern that we can, you can start to understand the different ways that people communicate and the different ways that software get developed in the cluster of those repositories that you depend on or are interested in, depending on how you want to bound your own ecosystem. And I just want to zoom out next on the next slide. And just again, we gather data at a very granular level, which allows you to zoom in on it on your repository, or zoom out and look at thousands of repositories at a time and how they differ from each other. And that is, and I would point you to Augur, our website, to the GitHub repository, and to the community reports repository here at the end. And at that point, I think we'll say thank you and take questions.
Hey, would love to say hi in face, but my video camera is down now. So so very interesting. I'm happy to see all these charts and diagrams. I'm actually particularly curious about when Matt said that metrics can be gamed. So I'm wondering if you have already seen some examples or real world scenarios and how that could happen. And it does, you do not need to, tell real names or something like that.
Yeah. I think that the metrics, if you look at our website, the metrics we've developed are mostly focused at the project level and on that Git repository. And I've seen them gamed, and we haven't defined metrics, but when people are trying to rank contributors and you get into these, I want to show the most commits or the most lines of code, I think that's the easiest game to get into in open source.
We're very interested in how our packages are being used out there, but a lot of that information is quite hard to come by. Like, we would like to know how many people install our packages, for example, but we can't get our libraries to phone home because that would be an unpopular move. Have you thought a bit about some of these problems where on how to obtain metrics like that you can only really get hold of in difficult ways?
I mean, it's for example, the number of clones is something that we're interested in, but you have to have certain rights on GitHub, for example, to get access to that data, as you point out. I think package managers can give us some of that information, but you're right. The downloads and the installs info is harder to come by for a lot of projects. I mean, Red Hat will count the ISOs that are downloaded, but does that mean somebody burned one, or does it mean they burned 100? It's very hard to count some of this.
So Stefan, I think one of the things that this raises is we can only see so deeply on some of the data. And one of the things that we say in the Chaos project is we're trying to move off zero. So we're trying to provide any more transparency than we may not have had yesterday. And so can we provide full transparency? Maybe not, but can we at least improve? And I think to your question too, like where I would see, we've actually talked about this question, and it ended up oftentimes in the value working group, which is trying to ascribe value to the project that you have through uptake. So I think there is a platform where this question is occurring, but getting that trace data can be tricky sometimes.
And that is one place that Augur can help you with a lot of trace data, but we the package managers, Sumana put a really nice link to how you can get your PyPy statistics into the shared chat. So there are ways to get some of the information. And a lot of that can be sort of added later or tracked, or we can import it. If there are particular package managers folks are interested in, we'd love to know that so we can build tooling around it.